Exercise 1.2 NCERT. Question number 1. Function fx is given as 1 upon x, where f is defined from to r star, that is domain and codomain both are r star, where r star is defined as the set of all the real numbers except 0, r minus curly bracket 0. That is, only 0 is excluded from all the real values, that is called the set of non-zero real values. So we have to check whether this function is a 1, 1 or onto or both. So let's start. Fx given as 1 over x for f from r star to r star. So first we have to assume two arbitrary elements x1 and x2 from r star such that fx1 is equal to fx2. Since fx is equal to 1 over x, then fx1 will be 1 over x1 and fx2 will be 1 over x2. So it implies that 1 upon x1 is equal to 1 upon x2. Taking reciprocal of both sides, we get x1 is equal to x2. So fx1 is equal to fx2 implies that x1 is equal to x2. That is, each and every element of domain has a distinct image in codomain, which is the criteria of 1, 1 function. Thus, f is 1, 1 function. Now we need to check subjectivity or onto-ness of the function. For that, we need to find out range of the function. So let y is equal to fx, that is 1 upon x. So this may be written as x is equal to 1 upon y. Now clearly, x is defined for all the values of y except 0, because for 0, x will be undefined. 1 upon 0 will be infinity. So x is defined for all y belongs to r minus curly bracket 0. Or we may say that y belongs to r star, because r star is given as r minus curly bracket 0. So range of the function is equal to r star. And codomain of f is also given r star. So f is onto function as well, since range of f is equal to codomain of f. Thus, we may conclude that f is 1, 1 and onto function. Now, question number 2, first part. Fx is equal to x square and f is defined from n to n. So let us check injectivity of the function first. For that, we need to assume two arbitrary elements, let x1 and x2 belongs to n such that fx1 is equal to fx2 implies that x1 square is equal to x2 square. Transposing x2 square to left hand side, we may write this expression as x1 square minus x2 square is equal to 0. Now, applying a square minus b square identity, we may write it as x1 plus x2 into x1 minus x2 is equal to 0. So now either x1 plus x2 is equal to 0 or x1 minus x2 is equal to 0. Now, since x1 and x2 both are natural numbers and sum of two natural numbers may not be 0, so this is invalid result. So we may call it absurd. We have only one valid result, that is x1 minus x2 is equal to 0, because difference of two natural numbers may be 0. So x1 is equal to x2. Thus, fx1 is equal to fx2 implies that x1 is equal to x2 only. So f is a 1-1 function. Or in other words, we may say f is an injective function. Now let us check surjectivity of the function. Let y is equal to fx, and here in this case fx is x square. So y is equal to x square may be written as x is equal to under root y. We have not taken plus minus under root y because x is a natural number and natural number may not be negative, it is always positive. So only positive sign we have taken and we have neglected negative sign. So now we have to think of for what values of y x is defined. So obviously for y is equal to 1, x is defined, for y is equal to 4x is defined, and for y is equal to 9, and so on. So x is defined only when y is a perfect square. Thus, the possible values of y will be the perfect squares of the natural numbers. So, range of the function will be the set of 1, 4, 9, and so on. But codomain of the function as given, that is set of natural numbers. So clearly range is not equal to codomain. And if range is not equal to codomain, then function cannot be an onto function, and thus we may conclude that f is not a surjective function. So from the above discussion, we may conclude that f is 1-1 but not onto. 1-1 function is also known as injective function, and onto function is also known as surjective function. So in other words, we may say that f is an injective function but not a surjective function. Now the second part of second question, a function is the same as the previous one, fx is equal to x square, but the domain and codomain are different because here f is defined from z to z. That is, domain and codomain both are set of integers. So if we check injectivity, and for that purpose we take two arbitrary elements x1 and x2 from domain z such that fx1 is equal to fx2. So it implies that x1 square is equal to x2 square, or x1 square minus x2 square is equal to 0, or x1 plus x2 into x1 minus x2 is equal to 0. So either x1 plus x2 is equal to 0 or x1 minus x2 is equal to 0. Now here x1 plus x2 is equal to 0 is a valid result which was invalid in the previous part, because in first part the domain was set of natural numbers and the sum of two natural numbers cannot be 0. But here the domain is z, that is set of integers, and integers are negative and also positive and 0. So the sum of two integers may be 0. So this is a valid result. So from this we get x1 is equal to minus x2, and second one x1 is equal to x2. So we have two possible results for fx1 is equal to fx2. If fx1 is equal to fx2, it implies either x1 is equal to minus x2 or x1 is equal to x2. That is, the function is not 1-1 function, because if function is 1-1 function, we can have only one condition for fx1 is equal to fx2, that is x1 is equal to x2. F is not 1-1 function. Now let us check surjectivity. Let y is equal to fx, that is y is equal to x square, or x is equal to plus minus under root y, Here we have taken plus minus because x is an integer and integer can be positive, negative or 0. Clearly, x is defined for y is equal to 0, 1, 4, 9, 16 and so on. Here again, x is defined for those values of y which are perfect squares. So we can say that range of the function is equal to curly bracket 0, 1, 4, 9, 16 and so on. But codomain of f equal to set of integers. Here again, range of f is not equal to codomain of f. Thus, f is not an onto function. Hence, we may conclude that f is neither injective nor surjective in this case. Now let us take third part, in which again the same function fx is equal to x squared, but this time f is defined from R to R. That is, domain and codomain both are the set of real numbers. So let us check injectivity first. Let x1 and x2 belongs to R such that fx1 is equal to fx2. So it implies that x1 square is equal to x2 square, or x1 square minus x2 square is equal to 0, or x1 plus x2 into x1 minus x2 is equal to 0. So either x1 plus x2 is equal to 0 or x1 minus x2 is equal to 0. Both are valid results because sum of two real numbers may be 0. Both results are valid. So we have either x1 is equal to minus x2 or x1 is equal to x2. So fx1 is equal to fx2 implies that either x1 is equal to x2 or x1 is equal to minus x2. Thus, f is not a 1-1 function. Now let us check surjectivity of the function. For that, we need to find out range of the function. So let y is equal to fx, that is x square, or x square is equal to y, or x is equal to plus minus under root y. But here x is defined for the non-negative values of y because x is a real number. So x is defined for all y belongs to R positive. R positive means all the non-negative real numbers, because for the negative numbers x may not be defined because under root any negative number is not a real number, that is imaginary number. So range of the function is equal to R positive, but codomain is equal to R. Thus range is not equal to codomain. And so f is not surjective. Thus we may conclude that f is neither 1-1 nor onto. Now fourth part. Now here we are given as fx is equal to x cube, where f is defined from n to n. Let us check injectivity. For that, we need to assume two arbitrary elements x1 and x2 from set of natural numbers such that fx1 is equal to fx2, x1 cube is equal to x2 cube, or x1 cube minus x2 cube is equal to 0. Factorizing using the identity a cube minus b cube, I write it as x1 minus x2 into x1 square plus x2 square plus x1 x2 is equal to 0. So either x1 minus x2 is equal to 0 or x1 square plus x2 square plus x1 x2 is equal to 0. So from the first condition we have x1 is equal to x2, but the second condition is invalid or absurd because x1 square is absolutely positive, x2 square is also absolutely positive, and x1 and x2 means the product of two natural numbers is always a positive number. So these three numbers are positive, so sum of three positive numbers may not be 0. So this is absurd. Thus, if fx1 is equal to fx2, it implies that x1 is equal to x2 only. So the criteria of one-oneness is satisfied, and we may say that f is one-one function or f is an injective function. Now let us check subjectivity of the function. Let y is equal to fx, y is equal to x cube implies that x is equal to cube root of y. Since x and y both belong to n set of natural numbers, so clearly x is defined for all y is equal to 1, 8, 27, and so on. That is, x is defined for those values of y which are cube of any natural numbers. So range of f is equal to curly bracket 1, 8, 27, and so on. But codomain of f is equal to set of natural number. Thus, range of f not equal to codomain of f. Thus, f is not a surjective function. Hence, we may conclude that f is injective but not surjective. Now, sum number 3, where fx is given as greatest integer function and f is defined from R to R. That is, domain and codomain of the function are set of real numbers, and we have to prove that f is neither 1, 1 nor onto, or in other words, f is neither injective nor surjective. Now, let us assume two arbitrary elements x1 and x2 from domain R such that fx1 is equal to fx2. Is that greatest integer function x1 is equal to the greatest integer function x2, which is possible even if x1 is not equal to x2. As for example, for any two consecutive integers a and b are two consecutive integers. So for any two elements belonging to square bracket a comma b open bracket, fx1 must be equal to fx2 if x1 is equal to x2 or x1 is not equal to x2. For example, in interval 1 comma 2 parenthesis, If we take two unequal elements like 1.2 and 1.7, so by the definition of greatest integer function 1.2 is equal to 1 and greatest integer function 1.7 is also equal to 1. So greatest integer function 1.2 is equal to greatest integer function 1.7, but 1.2 is not equal to 1.7. Thus, f is not an injective function. Now let us check surjectivity of the function. Let y is equal to fx, where y is equal to greatest integer function x. Since greatest integer function x always belongs to set of integers, so y belongs to integers. For all x belongs to R, for any real value of x, y will belongs to the set of integers. Thus, range of f is equal to set of integers z, but codomain of f is equal to R. Thus, range is not equal to codomain. Hence, f is not a surjective function. Hence, f is neither 1, 1 nor onto. Question number 4, fx is equal to mod x, where f is defined from R to R. So let us check injectivity first. Let x1, x2 belongs to R such that fx1 is equal to fx2 implies that mod x1 is equal to mod x2. It implies that mod x1 is equal to mod x2 is possible either x1 is equal to x2 or for x1 is, as for example, x1 is equal to 2 and x2 is equal to minus 2. So obviously plus 2 is not equal to minus 2, so x1 is not equal to x2. But modulus 2 is equal to 2 and modulus minus 2 is also equal to 2. So modulus 2 is equal to modulus minus 2. Thus, we may say that fx1 is equal to fx2 implies that either x1 is equal to x2 or x1 is equal to minus x2. Thus, f is not 1, 1 function. Now let us check surjectivity of the function. For surjectivity, we need to find out range of the function. So let y is equal to fx or y is equal to modulus x. As we know that modulus x is always greater than or equal to 0 for all x belongs to R. So y is always greater than or equal to 0. So the set of possible values of y is called range. Thus, range of the function is equal to square bracket 0, comma infinity. But codomain is given as R. So clearly, range of f is not equal to codomain of f. Thus, f is not onto function. Thus, we may conclude that f is neither on 1 nor on 2. Now the next question, that is the fifth one, f is defined from R to R and fx is defined as fx is equal to 1 if x is greater than 0, fx is equal to 0 if x is equal to 0, and fx is equal to minus 1 if x is less than 0. So let us check first injectivity, as f is defined from R to R and fx is equal to 1 if x is greater than 0 and fx is equal to 0 if x is equal to 0 and fx is equal to minus 1 if x is less than 0. So for all x1 and x2 belongs to 0 comma infinity. Since for x is greater than 0 means any value from 0 to infinity, fx has a constant value 1. So there are infinite real numbers from 0 to infinity. So any two numbers from 0 to infinity, and though they are equal or not equal, the function's value is the same. So fx1 is equal to fx2 is equal to 1 even when x1 is not equal to x2. So infinite numbers will have the same image in codomain 1. In the same way, for all the values of x1, x2 belongs to minus infinity to 0, that is all the values from 0 to minus infinity, fx1 is equal to fx2 is equal to minus 1 if x1 is not equal to x2. So f is not 1, function. Now let us check subjectivity, which is quite simple because fx can have only three values, that is 1 or 0 or minus 1. So the possible values of fx are only these three values. So range of f is equal to curly bracket minus 1, 0, 1. But codomain is given as R. It implies that range of f is not equal to codomain. Thus, f is not an onto function 2. Hence, we may conclude that f is neither 1, 1 or injective nor onto or surjective. Now question number 6. A is given as a set of three numbers 1, 2, 3 and B is given as the set of four elements 4, 5, 6, 7. And F is defined in roster form as the set of ordered pairs 1, 4, 2, 5 and 3, 6. And F is defined from A to B. And we need to prove that F is 1, function. This is domain A. And suppose this is codomain B. There are three elements in A, that is 1, 2 and 3. And in codomain there are four elements. One is 4, second is 5, third is 6 and fourth is 7. 1, 4, that is image of 1 is 4. 2, 5, that is 2 is related to 5. 3, 6, 3 is associated with 6. So as you see, each and every element of domain has a distinct image in codomain. Since every element of domain A has a distinct image in codomain B. Therefore, f is 1, function. Now the seventh one, first part, where fx is equal to 3 minus 4x, and f is defined from R to R. Now we have to check whether it is bijective or not. So let us check first injectivity. Let x1, x2 from domain R such that fx1 is equal to fx2 implies that 3 minus 4x1 is equal to 3 minus 4x2. Positive 3 is cancelled by positive 3 minus 4x1 on the left and minus 4x2 on the right. Now simply this is cancelled by minus and 4 is cancelled by 4. We have x1 is equal to x2. So we may conclude that fx1 is equal to fx2 implies that x1 is equal to x2 only. Thus, f is an injective function. Now let us check subjectivity. Let y is equal to fx, or y is equal to 3 minus 4x, or 4x is equal to 3 minus y, or x is equal to 3 minus y upon 4. Clearly, x is defined for all y belongs to set of real numbers. That means for every real value of y, x must be real. The range of f is equal to R. Codomain of f is also equal to R. Thus, range is equal to codomain. So, f is a surjective function too. So, from above discussion, we may conclude that f is bijective function because it is 1, 1 as well as onto. The second part of question number 7, I'm leaving for the students, so you should try yourself. Eighth, here f is given as a function from a cross b to b cross a, such that f a comma b is equal to b comma a. So we have to prove that this is a bijective function. So let us talk about injectivity. F is from a cross b to b cross a. Let us assume arbitrary elements as a1, b1 and a2, b2 from a cross b, such that f a1, b1 is equal to f a2, b2. As by the definition, f a comma b is equal to ordered pair b comma a. So f a comma b1 must be equal to ordered pair b1 comma a1. Similarly, on the right hand side, f a2 comma b2 must be equal to ordered pair b2 comma a2. So it implies that ordered pairs may be equal when their corresponding elements are identical. So it implies that b1 is equal to b2 and a1 is equal to a2. So it implies that a1 comma b1 is exactly equal to a2 comma b2. Thus, f is an injective function. Now let us talk about surjectivity of the function. Since f is defined from A cross B to B cross A, so since A cross B inverse is equal to B cross A, it implies that for all A comma B belongs to A cross B, there must exist an ordered pair B comma A in B cross A. So, for all B comma A belongs to B cross A, there exists A cross B in domain A cross B such that f A comma B is equal to B comma A. So, the range of f must be equal to B cross A, and codomain is also the same, so it implies that range is exactly equal to codomain. Thus, the function is onto as well, so we may conclude that the function is a bijective function as it is 1 as well as onto. Now the question number 9, for all n belongs to set of natural numbers, the function fn is defined as n plus 1 upon 2 if n is odd and fx is equal to n upon 2 if n is even. Here we have to examine whether the function is a bijective function or not. So let us check injectivity first. Let n is equal to 1, which belongs to set of natural numbers, and since 1 is odd, so when n is odd, fn is equal to n plus 1 upon 2. This condition is applied. We have to substitute n is equal to 1 in first condition to find fn. So the value of fn is equal to 1 plus 1 upon 2, that is equal to 1. Now if n is equal to 2, which also belongs to natural number, but this is even, so if n is even, fn is equal to n upon 2, this condition is applied for this, and we have to substitute n is equal to 2 in the second condition to find fn. So fn is equal to 2 upon 2, that is equal to 1 again. So f1 is equal to f2, though 1 is not equal to 2. Thus, f is not 1 function. And since we were supposed to find whether it is bijective function or not, and when it is not injective, it cannot be bijective function, so there is no need to check surjectivity of the function. Here we may write the conclusion that f is not a bijective function. Now the last question, that is 10th one. Here A is given as set of all the real numbers except 3, and B is given as set of all the real numbers except 1, and fx is defined as x minus 2 upon x minus 3. Now we have to examine whether f is bijective or not. Let x1 and x2 belongs to A, that is domain, such that fx1 is equal to fx2, implies that x1 minus 2 upon x1 minus 3 is equal to x2 minus 2 upon x2 minus 3. It implies that if we cross multiply, we have x1 minus 2 into x2 minus 3 is equal to x1 minus 3 into x2 minus 2. Now we have to multiply these two brackets together. X1 into x2, x1 into minus 3x1. 2 minus 2 into x2 minus 2x2 minus 2 into minus 3 plus 6 equal to x1 into x2, x1 into minus 2 minus 2 x1 minus 3 into x2, that is minus 3 x2 minus 3 into minus 2 plus 6. Now clearly from right hand side and left hand side, x1 x2 and positive 6 on both sides are cancelled with each other. Here minus 3x1. Now transpose this minus 2x2 to left hand side, it becomes positive on transposition, plus 2x1. And on the right hand side, write down this minus 3x2 and then transpose this term, that is minus 2x2 to right hand side, so it becomes positive on transposition, that is plus 2x2. Minus 3x1 plus 2x1, that is minus x1 is left on the left, and minus 3x2 plus 2x2, then minus x2 is left on the right. Minus is cancelled by a minus. We have x1 is equal to x2. So we may conclude that fx1 is equal to fx2 implies that x1 is equal to x2. So fx is an injective function. We have to find out the range of the function and assume first y is equal to fx. That is y is equal to fx, which is x minus 2 upon x minus 3. Transposing x minus 3 to left hand side, it will multiply y is equal to x minus 2. Open bracket, then y will multiply both the terms. We have xy minus 3y on the right hand side, x minus 2 as it is. Now transpose x to left hand side and this term minus 3y to right hand side. We have xy minus x is equal to 3y becomes positive on transposition to right hand side, minus 2 as it is. Now taking x common out of these two terms, we have x y minus 1 is equal to 3y minus 2. So we get x is equal to 3y minus 2 upon y minus 1. Clearly, x is defined for all the values of y except y is equal to 1. So x is defined for all y belongs to R minus curly bracket 1. So 1 is excluded, so that is minus curly bracket 1 and except 1. Each and every real number is possible for y for which x is defined. So range of f is equal to r minus curly bracket 1. But r minus curly bracket 1 is given as set B. So we may write it as B. And B is the codomain because f is from A to B. So codomain is also B. Range of f is exactly equal to codomain of f. Thus, f is an onto function. Thus, from above discussion, we may conclude that f is 1, 1 as well as onto function. Hence, f is a bijective function.